Hello, good afternoon, and welcome to today's class. In today's class, I'm going to share with you a very beautiful uh, a distribution, and this is called the gamma distribution. I'm going to show you how you can see this distribution and recognize them, and then at the same time, you can be able to extract from this distribution the mean and the variance of this distribution, given that I'm going to deal with the two-parameter gamma distribution. So I'm going to still show you something about the one gamma distribution, though you can try something about it. All right. So the objective here is that you'll be able to see and recognize the nature of a gamma distribution anywhere you are. Then two, you'd be able to derive the PDF of this gamma distribution if you can follow this tutorial. Oh, very well. And number three is that you'll be able to derive the mean and the variance of this distribution, as I said earlier. So, before I proceed, I would like you to, if you do not subscribe to my channel, please do well to subscribe to my channel, comment and like, so that when subsequent of this kind of video comes up, you'll be able to have access to it. You'll be able to also have what I want. You know, I have needs here. All right, so to start up, I will say that by definition, the gamma distribution is given by this. So the gamma distribution, gamma of alpha, I use the Greek word alphabet alpha. Gamma of alpha is equals to the integral. So the limit is from integral from 0 to infinity. Then I decide to use y. You can use anything. So y raised to the power of alpha minus 1 exponential minus y, and the y is always known as the gamma distribution. So from this gamma distribution, I'm going to derive the PDF of this gamma distribution with two parameters in this case. So, but before we also proceed, I would like you to know another form of writing this stuff. So gamma of alpha is the same thing as alpha minus 1 factorial. And I want you to know what this means. So it's a factorial moment, it's a factorial multiplication. So if I have something like gamma of 2, I can say this is 2 minus 1 factorial. That will give us 2 factorial, 1 factorial, which is equals to 1, which is equals to 1. 1 factorial, that is 1 times 0, 1, which is 1. So, and if I have like gamma of 5, this is 5 times 4 times 3 times 2 times 1, which is going to give us, this is 20, and this is the this is 20, and this is 60, this is 120. Okay, but this is not what we are going to do right now. So I'm trying to show you that if you have something like gamma of alpha, and you are able to write it like gamma of alpha, this is the same thing as alpha minus 1 factorial, which we can also write it as alpha minus 1, since it is a factorial stuff, times alpha minus 1, which is alpha minus 2, times alpha minus 3, anywhere I want to stop. So I can say dot, 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 times alpha minus n plus 1, then factorial. So wherever I want to stop. So that is what I'm trying to show you first, because you are going to see this coming in our subsequent lesson. All right, so also alpha plus gamma of alpha plus a is equals to alpha plus minus 1 or factorial, for a being a number from 1 to any number in infinity. Okay, so to proceed with our lesson for today, the objective 2 is to find the PDF of this gamma distribution. So gamma distribution being equals to integral from 0 to infinity y raised to the power of alpha minus 1 exponential minus y dy. So I title as question 1. I'll say let y equals to x over beta. I like to use this notation. So I will differentiate this equation 2, and I will have this. The derivative of y must be equals to 1 all over beta derivative of x. If you like, you can call this 2 asterisk. So I'm now going to substitute these 2 and these 2 asterisk into 1, substituting into 1. If you substitute all of this, now that means any place you see y, you replace it with this, and any place you see the y, and you replace it with this. So by doing so, we have gamma of alpha, which is here, equals to integral from 0 to infinity. Then in place of y here, we replace it with x over beta, raised to the power of alpha minus 1, exponential minus y. So y there still become x upon beta. Look at it here. Then times the x, I mean the y, and the y is given as 1 upon beta. The x I've given it here. So you can see all the substitution. All the substitutions are here, and then here, and then here. Okay. So now I'll evaluate that. From indices, this place will come here, exponential minus x upon beta, then divided by beta raised to the power of alpha minus 1, which is when you open this place here, the power exponent here, which is alpha minus 1, is going to affect both the x and the beta here. Then times 1 upon the reciprocal of beta that is here by the x side. So that will come directly to where the beta is here. So both of them will multiply. So automatically you have something like beta raised to the power of alpha times beta, which is the same thing as plus 1 on the exponent. So that will give us beta raised to the power of alpha. That's how we get to here. So, and we have here. So for any PDF to be a valid PDF, remember that the integral from its station bound minus infinity, for example, to infinity of that PDF f of x must be equals to a unity, like 1. So for that reason, I'm going to divide all through by gamma of alpha here, gamma of alpha, divide this equation, this place here, by gamma of alpha. Well, if I divide all through by gamma of alpha, then we will have what we have here, exactly here. So, and do the necessary substitution and pull out the constant gamma of alpha and beta raised to the power of alpha, which is inside the integrand, out, and then we have reciprocal of them. Then gamma of alpha divide gamma of alpha, you have 1. So therefore, we have that the integration here, pulling everything inside the integration, it means that the integral from 0 to infinity of x raised to the power of alpha minus 1, which is here, then exponential minus x upon beta, which is here, look at it there, divided by, I pull this constant here, 1 over gamma and alpha here, into the integrand here, look at them, divided, the x, which is here, all of them, since we divide alpha, gamma of alpha by gamma of alpha, that is 1 time, so we have 1. Meaning that what we have here inside of this integrand is a valid PDF of this particular distribution. Okay. So I said that that is a criteria for a valid PDF. For a PDF to be a valid one, the limit of that domain must, of it, if you integrate it over that limit, it must be equals to 1. So this equals to 1, so this must be the valid PDF with 2 parameters, alpha and beta. So that is exactly what I've written down here. For all x that is greater than 0, meaning all the variable of x, value of x must be equal to 0. So obtain our first objective, meaning that the PDF of the gamma distribution is 1 upon gamma of alpha, beta raised to the power of alpha, x raised to the power of alpha minus 1 exponential minus x upon beta. Okay. All right. So to find the mean, that expectation, that is the first moment. By definition, expectation of x which is the first moment, must be equals to integral of that boundary, that domain, is integral from 0 to infinity in this case, remember, of the x itself, since we are finding the expectation of the x, then the PDF, then the x. This is true for all continuous function. So, and evaluating this out, we have integral from 0 to infinity. This x, look at it here. Then the PDF, as we derive in our equation 3, you can see that's the PDF, then the x. Look at that there. So now we evaluate this, move out all the constants from the integrand. We move them out and we have them here outside. So, and then we deal with the integration explicitly. So we have x raised to the power of alpha minus 1 times x, which is to the power of 1 here. So if you carry out that indices, you have x raised to the power of alpha plus 1, then minus 1. What I will advise is don't evaluate this place. Don't say that this equals to 0. Just maintain it. I'm going to tell you the reason. Instead, enclose this with bracket. So we have here, that's what I'm saying. Then exponential minus x all upon beta dx, which I'm repeating what is there. Now I'm going to do it. Why I'm not evaluating this place is this. Remember from the beginning of the class here, we have that the gamma of alpha, gamma function itself, gamma distribution says that gamma of alpha equals to integral from 0 to infinity y raised to the power of, I remember saying that you can use any of the variable of your choice. Y is not constant there. So you have y alpha minus 1 exponential minus y and the y. So what I want to do here right now is to make this place here to make that place there to look exactly as this place here. All right. So how do I do that? First, I will let I'm introducing another variable, to be equals to x upon beta. Remember, x has a boundary from 0 to infinity. So if you want to check for the validity of the limit, whether it's still the same, so if x equals to what you see there, and by making x subject of the formula, it means that beta u, which is the same thing as x, must lies between 0 and infinity also. So if I divide all through by beta, all through by beta, 0 upon anything is 0 by u, then by infinity divided by anything is still infinity. So that means the new variable still have the limit from 0 to infinity. Nothing has really changed. So still that's why I'm still writing it. I'm going to still write it 0 to infinity. So I let u to be equals to x upon beta. That is what is on the exponent here of the exponential function. Then I make x subject of the formula, so that I will do a substitution here in the 5. Then I'll take the derivative of u and the x, and this is what we have. So just like before, I'm going to do the substitution into equation 5. So if I do the substitution into equation 5, not 1, into equation 5, then we have 1 upon gamma of alpha, beta raised to the power of alpha, integral from 0 to infinity. In place of x, I'll write beta u, raised to the power of alpha plus 1 minus 1 there. Exponential, in place of x upon beta, I write u, since u equals to that. Then in place of the x, I write beta du. Look at it here. Now I'll carry out the evaluation of that. I evaluate that, simplify everything. This is beta here. Remember, everything here is by multiplication. So if you bring this close to here, the multiplication will introduce an index plus 1, which will take care of minus 1. So we are left with beta raised to the power of alpha plus 1. And beta is a constant. So I'm going to move it out of this region of integration and pull it out to be where you have all the constants. Then we are going to also be left with u raised to the power of alpha plus 1 minus 1 exponential minus u, then du. That's exactly what we have here. This is what I'm talking about. So you can also see that we do a similar thing like what we did. And if you compare here, you see this is like integral from 0 to infinity. This place now really resemble this place. So since integral of 1 alpha here is equals to gamma of alpha, integral to 0 to infinity, that means I can write here is still a gamma distribution with the parameter being alpha plus 1. So that means I can replace here this, what I'm just circling here with green. I can replace here with gamma of alpha plus 1. So also remember, I talk about the another way of writing gamma of alpha that is the same thing as alpha minus 1 factorial. So we have here turned to this, and here turned to this, which I'm still going to change it to this. So we have alpha plus 1 minus 1 factorial, just like I turn alpha to alpha minus 1 factorial. So alpha plus 1 will turn to alpha plus 1 minus 1 factorial. So, and here is indices here, alpha, beta raised to the power of alpha plus 1 is the same thing as beta raised to the power of alpha times beta. So we have that there. We evaluate everything and take it again and again. And we have at the factorial moment, it's become exactly what we have on the denominator. So the alpha minus 1 on the numerator will cancel the alpha minus 1 on the denominator. So we are left with alpha and beta as the product of themselves. So that simply means that the expectation of x, which is the same thing as the mu, is equals to the product of the two parameter, alpha, beta, for any value of alpha and beta. So it's called the first moment, and so on and so forth. So similarly, we want to find, as the last objective of this particular tutorial, we want to find the variance var of that. And variance by definition is equals to the expectation of x squared minus expectation of x all squared. So remember, we've gotten the expectation of x already. So that means we can put this here and square the result. And then all we need to do here in order for us to be able to find the value of the variance of x is to obtain the value of the expectation of x squared. That's the second moment. So we say that the expectation of x squared by definition is equals to expectation of x squared by definition, just like expectation of x is x squared integral from 0 to infinity. That is the limit of that domain, x squared f of x and then the x. All right. So if you like, consider equation 8. Then I'll go ahead to do similar thing that we did for expectation of x. So remember that here is the f of x, that is the PDF. Here is the x function, the x variable, and then this is the derivative, which we are going to deal with them explicitly. So this is the PDF appearing here. So I'll substitute the f of x with the PDF, and then I remove out the constant terms there outside the integrand. Then I deal with the x squared and the x raised to power alpha plus 1, and that becomes here, just like we did for the expectation of x. And then for me to make this place to also look like the gamma function, like the gamma distribution function, so we decide to also do a similar thing that we did to the expectation of x, just to make this place look like a gamma function so that we can write this place in gamma notation. So I let u to be equals to the x all over beta, and then make x subject of the formula, take the derivative of u respect to x, and then do the substitution into the equation 9, and we have here. Then after this, we evaluate out just like before. This is a beta function here. This is a beta function there. This is a beta function that I move from here down close to where this one is. Opening this bracket, the index here will affect both the beta and the u. So that's why I'm writing them out explicitly. So, and then the beta here will go with the power of exponent 1. So by the time this exponent 1 deal with exponent minus 1, they will diminish. So what we'll have as the power of the beta is alpha plus 2, which I'm going to move out of the integrand. And we're going to have it here. Then we have u raised to the power of alpha plus 2. Look at it here. Then minus 1, which is here, exponential minus u. So the whole of this place combined with the integral from 0 to infinity become a gamma distribution, which is equals to gamma of alpha plus 2. Look at it here. I'm talking about here now. So this become this. Just like before, this become this. We can another form of writing it. And gamma of alpha here become this. And then we take the factorial product of here and we have here. So all of this here is the same thing as here to here. From here to here. Then, and we can see that the denominator has appeared on the numerator. So there and there can go, they cancel. So we are left with beta squared times alpha into alpha plus 1. Look at them here. So therefore, we said that the expectation of x squared is equals to alpha beta squared into alpha plus 1. So we obtain the value of the expectation of x squared now. So the next thing is to substitute that value into the variance formula. So putting it in the variance formula, we put here and we drop the expectation of x. Remember, it was equals to alpha beta. So substituting it into a way we have expectation of x, we have alpha beta all squared, which become alpha squared beta squared. And then we open this bracket, this time this we have alpha squared beta squared plus this time this we have alpha beta squared. This and this are like them, so they go 0. We are left with this. So therefore, we can see that the variance of a gamma distribution of the first kind is equals to this. So that is, we've been able to also meet up with all our expectations and our objectives. So I would like you to not just subscribe to my channel, make sure you follow the tutorial and one is going to help you in your statistic field and for some people that are doing distributions. Okay, if you did not subscribe to this channel, please, I would like you to help and do the subscription and also thumbs up if the tutorial makes sense to you. Like and don't fail to comment, it makes sense to me. And if you have any question pertaining to here, don't fail to drop it on my comment section because it will help me to know the direction where I can solve your own personal problem. All right, so I will say thank you for your time.